Okay, hello colleagues. Let's begin our webinar today. Hello again. Welcome to the fifth webinar in UNICEF's webinar series on data collection, which is organized, as you know, by the Data and Analytics section at UNICEF headquarters. I'm Attila Hancıoğlu, Chief of the Data Collection Unit in the Data and Analytics section. Our webinar today is on remote sensing data by Paul Aplin of the Edge Hill University. As with previous webinars, let me remind you that this webinar is also being recorded and will be posted on our SharePoint site. You can find the link at the very end of the emails that you received. Today's webinar is 1 hour. Throughout the webinar, please remain muted, but please place your questions in the chat box. We will have a Q&A segment at the end to answer your questions. And with this, without further ado, I would like to hand over the floor to my colleague, Toby Wicks, who will first introduce himself and then facilitate the session. Toby?
Thank you so much, Attila. Can you hear me okay?
We can hear you well. Thank you very much.
Wonderful. So as Attila said, I had the pleasure of working alongside him, UNICEF headquarters in New York. My name's Toby. And for my sins, I have a PhD in remote sensing. So when I put my hand up to help with this session, Attila kindly agreed. And it is my delight to host Paul Aplin with us this morning. Paul really needs no introduction. I think if you're here with us today, you've already seen the invitation and therefore you've had a chance to read Paul's bio. Like most academics, Paul has quite a humble bio. And in fact, we are terribly fortunate to have him with us today because really he is a very big name, not only in the UK, but globally in terms of both remote sensing and in particular land cover classification. So we'll have the next 30 minutes or so listening to Paul in terms of an introduction to remotely sensed data. Paul, for your benefit, there's quite a crowd online today. So we're with about well over 70 participants, a few of whom indeed have a little bit of exposure to remote sensing, even a couple of PhDs in that audience. But with that, Paul, I think we'll have the next half an hour or so listening to insights from you in and around remotely sensed data. As Attila has said, colleagues, feel free to, if you have questions, put them in the chat. And I think we'll have plenty of time when Paul is finished for an in-depth conversation in and around remotely sensed data. So with that, Paul, over to you.
Thank you, Toby. Can you see me and hear me?
We can see you and hear you loud and clear.
Good, okay, thank you. Thanks very much. Thanks for that gracious introduction, Toby. I'm not sure I would call myself at all humble, but it's very nice of you to say so. Okay, I thought I'd start with an example today. So thinking of what UNICEF partners and representatives would be interested in, I thought I'd start with modern slavery. I guess this is the kind of application, not necessarily the typical application I work in, but the kind of application that you might be interested in here. So I just want to show you an example of a couple of images to start with. And modern slavery is clearly a very significant concern, a humanitarian concern in the world today. It's everywhere. I'm based in the UK, and there's plenty of discussion about modern slavery existing and taking place in our country. And remote sensing has been applied to this. It's quite an interesting application in that regard, perhaps not the first one you think of. But for instance, different categories of modern slavery have been considered. And where there are large-scale industries that tend to be unregulated and rely quite heavily on effectively slave labor, it is possible, and often these are remote locations, often tucked away. It's quite difficult to get information on them, but it is now possible to use some remotely sensed imagery to investigate these. So here's just a couple of examples. This is an image showing Peru and showing mining sites, particularly gold mining, taking place in fairly remote parts of the country. and it's very apparent, it's very clear, loud and clear on the imagery what you can see. In South Asia, there's a South Asian brick belt. Brick manufacturing is very highly unregulated, and the infrastructure associated with brick making is very distinct. The brick kilns that you can see here, or the brick kilns that you can see here in the center of the picture, are very typical, very characteristic, and with very high resolution, easy to identify. It's hard to pinpoint every individual case. Clearly, these things are dispersed and remote, but these are large-scale industries. And we are now having quite a bit of success in identifying the location of brick manufacturing sites throughout. These ones are in India, which can then be subject to further inspection to find out the regulation backstory and whether slave labor is being involved. So I'll drop back to an introduction to remote sensing. I am an academic. I give lectures to my students on topics, and remote sensing is my pet topic. So I will be giving you, I hope it's appropriate to give most of you some basic instruction in what remote sensing is. I want to start, this is all online, it's all virtual, it's all digital, but remote sensing is a physical thing. This is a remotely sensed image. This is an image of San Ponsac wetland in Panama, and it's a laminated field sheet which I took on fieldwork there. I work in tropical peatland environments, and I'm showing you this physical copy for a reason. So I will come back to it later. It will all be explained a little bit later on, but that is an image, and you see also a hemispherical image of the Earth. There aren't actually many of hemispherical images of the Earth. They were only taken by shuttles en route to the moon. It's not a very typical image. And we're familiar with Earth observation and the idea of satellite images, I think. So a few definitions for you. Campbell and Wynne, one of my usual go-to textbook. I was asked to suggest some reading in relation to this webinar. My go-to text is Campbell and Wynne. This is the 3rd or 4th edition, I think, from 2011. Simply defining remote sensing as gathering of information at a distance. So it's quite an accessible thing. Stepping up the technicalities, we'll go to Mather and Koch. Mather is Toby's old undergraduate professor. The interpretation of measurements of electromagnetic energy reflected from or emitted by a target from a vantage point distant from the target. So it's the mechanism we use, it's light waves that we use to build up these images. And then I did manage to shoehorn a definition a bit more down to earth into this introductory lecture that I use for my students, staying as far away from the problem as possible. So I want you to remember that. I want you to remember staying as far away from the problem as possible, and my hard copy image. I will return to these at the very end of the lecture. So 50 odd years ago, we had one remote sensing satellite it was eventually called Landsat. It wasn't initially, actually. And it collected medium resolution satellite imagery, initially about 60 to 80 meters resolution. Later on, 30 meters resolution was the norm for most of the Landsat sensors. And you might be familiar with Landsat. I'm hoping most of you will have come across Landsat. Most of you will be familiar with this sort of image. And this is the stock remote sensing image that we have. Fast forward 50 odd years, about 45 years in the case of this slide. And you can see there's a lot more going around. This was a few years ago. It's been added to significantly, especially by the Sentinels mission in Europe. Since then, basically, there's lots of technology up there collecting lots and lots of data of lots of different properties of the Earth's surface and atmosphere and subsurface in some cases. So there's a lot of data available. And in these COVID times, I understand why UNICEF is looking into this issue of data. How do you get data when we're very restricted in what we can access on the ground? So I think, and I don't know your application areas terribly well, but there are good opportunities for use and reuse of image data, spatial data from some of these sources. So I'm going to take you through a handful of these. So I've started by introducing or mentioning Landsat, which I think many of you will be familiar with, but there's a lot more to it than that. So on this slide, so we've got our satellites. I'm spending most of the time talking about satellites, but also there are plenty of aircraft, airborne platforms used to collect imagery, and often that sort of imagery will be very, very highly detailed. And more recently, the new kid on the block is drones. So I'm not going to say much about drones. I think you'll be having another webinar specifically on that topic. So I'm going to steer a little bit clear of that. But there are many benefits to the versatility of drone use. The cost is very low cost, and the quality and detail of the data, because you're close to the ground, is really very good. So there's various platforms that can be used. And there's also various different sensing devices. So the Landsat-like passive optical sensor uses the sun's rays reflected off different features on the surface of the Earth being received by a satellite. So it's passive absorption of electromagnetic energy coming from the sun reflected off the Earth's surface. But there's also active remote sensing, and a couple of obvious examples include radar, so microwave remote sensing. And these are devices that send a radar signal out, much like in radar navigation, and they record the return signal after it's bounced off whatever feature it reaches. And the benefit of radar or microwave remote sensing is, or one key benefit is its very long wavelength, means it's not reliant on the sun's energy, and it can see through cloud, it can see through the atmosphere. You can always get an image, no matter what the weather is, and you can get an image day or night as well. So radar imagery is very useful in that regard. And then more recently, LiDAR, laser scanning instruments, are collecting very detailed elevation models of the surface of the Earth. Usually LiDARs are flown on board aircraft, but there have been a few cases, a few examples of satellite missions using LiDAR, most recently JEDI from the US. So that's the sensors and the platforms, and these are the data. So I've shown you a Landsat image, which is the typical optical image using visible wavelengths and infrared wavelengths used up to build a multi-spectral, a colored image of the Earth's surface. But there's also radar images. This is a black and white radar image showing the topography of an area. On the right-hand side, we have a LiDAR derived elevation model showing very great detail in an urban environment. We've got thermal sensors. So this is an urban heat island in London. So we can identify the temperature of the setting, and that is linked very strongly and very closely to human health issues and things like that. We've got nighttime lights information. Another US instrument routinely provides, or series of instruments routinely provides this sort of detail, this sort of information, which shows anthropogenic light pollution at night and is very useful for identifying where energy is, but also where population is, according to that. Or even if you know where populations exist and their differences around different parts of the world, what is the energy infrastructure to support those populations? So if I had an image, this is Western Europe or much of Europe. If I had an image of Africa, there would be significantly fewer of these very bright spots because there's less energy use and energy availability there. And then we've got very high resolution images in the most recent generation of satellite instruments and also from aircraft. We can see lots of detail, and this is especially where I think there's going to be good value for the UNICEF community to use. So what's good about remote sensing? What are the characteristics of the data which are beneficial? And there's quite a few. First, this very large area synoptic coverage, global coverage of the Earth via lots of different instruments, especially those that have sort of broader swaths. But even with a relatively narrow swath, and this is Sentinel-2, and I've put this up. This is one of the European Sentinel missions, which is sort of not a competitor, but an equivalent to the US Landsat series. This is a graphic of the Earth showing the tiles that make up every Sentinel scene. So we get coverage of the full Earth surface at quite a high resolution. Sentinel goes up beyond Landsat's 30 meters, up to 20 or 10 meters multispectral imagery. So global coverage is one benefit, giving you wall-to-wall coverage of any location that you're interested in. And these medium resolution Landsat and Sentinel and other instruments like MODIS, which has broader, bigger pixels, 250 or 500 meters and much larger area coverage. These medium resolution instruments are very good for large area monitoring. I'm an environmental scientist. I'm more interested in kind of natural or semi-natural distributions around the world. And these are a handful of slides that I used in a public lecture to promote the use of imagery in proving that environmental change was taking place. I gave a public lecture. It was called "No, Donald," guess which Donald, global warming is not an expensive hoax, see? And then I showed these series of images to try and prove this. So around the 1990s, remote sensing proved that the long suspected deforestation going on in the Amazon was taking place. And you can see the characteristic herringbone pattern of deforestation taking place here in the middle and right-hand images. That's land. Let's go into the sea, and we can do global monitoring of large-scale marine phenomena like El Nino and La Nina, the Southern Oscillation in the Pacific Ocean. And these images show the contrast between in sea surface temperature, white and red are very high or relatively high temperatures, blue and purple are relatively low temperatures. You can see the contrast between the La Nina episode on the left and El Nino on the right. And these data, this scale of imagery is captured every day. It's quite coarse spatial resolution, but very large area coverage. And the instruments that capture these data get around the entire Earth's surface every single day. So we can get this sort of information that frequently. We'll go to the atmosphere. I like to think that remote sensing discovered the ozone, the now famous ozone hole. And here's a contrast over a few decades. So in the 70s, 80s, there was the beginning of a problem with the ozone caused by CFC gases in the atmosphere, eroding away the valuable, essential ozone layer, which keeps out ultraviolet radiation, which is very harmful for our skin, for instance. And you can see how significantly the ozone hole has developed by the 2000s. And this hole now is permanent. It oscillates a little bit. We seem to have it under control, but remote sensing is able to show us this large scale environmental phenomenon. And finally, we'll go to an icy environment, to the cryosphere, and just look at glacial retreat. This is Columbia Glacier, a bit of a sort of a picture postcard for environmental change. This is a fairly charismatic glacier used for that purpose, but you can see the Columbia Glacier has retreated tens and tens of kilometers over 2 or 3 decades. And this is an example of the process of glacial retreat that's going on around the world. Okay. So just to tell you a little bit about what I do, one of the things I'm most recently interested in is tropical peatlands. I work in tropical peatlands environments. I've shown you my image already. I work in Panama, but also in Malaysia and Southeast Asia. And I'm particularly interested in the conversion of very valuable tropical peatland environments to other human land uses. And especially significant here is oil palm plantations. Palm oil is a now ubiquitous and still growing product that's used worldwide. It's cheap, it's efficient, and it's good in some ways. It brings a lot of labor and some economy to parts of the world where, you know, revenue is needed, jobs are needed, but it is very problematic environmentally. And here we've just used some image data to isolate the peatlands and then show where conversion has taken place over the last quarter of a century or so. And the red areas identified here are new oil palm within that time. And the colored areas is the totality of peatland, tropical peatland in Southeast Asia. So this is a really rapid process. It's something to be really concerned about. Peatlands, tropical peatlands especially, are very significant in retaining carbon and therefore the process of climate change. Just to sort of roll on from there, most recently in environmental science and in use of remote sensing, especially large area remote sensing in environmental analysis, we've started talking about essential climate variables, ECVs. These are properties representing the natural environment, both from in terms of the atmosphere and on oceanic surfaces and on the terrestrial land, that give a kind of a picture of how the environment is doing, how climate is doing. And the variables, the ECVs mentioned in the table here, this is from the European Space Agency, show all of the ECVs that are derived from some form of remote sensing imagery. And these are routinely acquired, processed and served up so that we've got ongoing monitoring of these very important properties to get an understanding of how the climate is and how it's changing through time. So I've shown this graphic before, but to express another positive trait of remote sensing, talked about global coverage earlier on, remote sensing provides data continuously, repetitively, in a structured and regular schedule, so that you know you're going to get updates, you know you're going to be able to get more data to compare against the data you got today and yesterday and last week and last month. And as I showed you, there are some sources of data that require global coverage every single day over quite wide areas. There are other more detailed instruments like Sentinel medium resolution satellites, which have these 10 or 20 meter bands, 10 or 20 meter multispectral bands. And Sentinel-2 can acquire all these tiles. So there's two satellites, Sentinel-2A and Sentinel-2B, can cover all of this area every 5 days. So we get a global update every 5 days. So you know where the data are, you know when they're coming, and thus you can plan to put these data into your processing chains and know that you're going to get useful information out the other end. And monitoring change over time is one of the most significant and commonly used techniques in remote sensing in image analysis. We now have capacity to monitor change over time, over varying timescales, over varying frequencies, according to the repetition with which imagery are required by any given sensor. And modern sensors have very high spatial detail, but also they can tilt and can typically get you coverage of any location every 2 or 3 days in most parts of the world. So you can get data regularly over time, but actually we can also think about going back in time. We now have this 50-year Landsat archive of data that we can mine and do retrospective analysis. So comparing what we've got today with what we had in the past. And here's a really nice graphic. I grabbed a lot of these graphics off the web, as you can imagine. And this is a really nice example of a tile of what was initially secondary evergreen forest. So this pixel here, where the arrow points, is represented by the cells here. And this is a sequence over time going from 1984 to 2016. And when it's blue, this is this pixel living life quite happily as an evergreen forest without any interference, without any change. Then around 2000, 2001, bang in the center of this pixel, it's a 30-meter pixel, a road, an access road was laid. And then in 2002, the pixel was clear cut. And you can see it's turned from blue to red. The timber was harvested, basically. And then for the remainder of the time, you can just see regrowth of the forest, getting back towards, now we're getting towards the bluey color that we started with, showing that the forest is coming to a sort of mature level again, and it won't be so long before it's harvested again, and then the cycle goes on. So we've got this incredible archive of data that we can use to monitor change over time, and we can also use it to forecast the future. So image data can be plugged in to various different types of geospatial analysis. A common approach is to use cellular automata to come up with scenario prediction on the basis of input variables. And this is a piece of work that I've done with some colleagues in China on urban ecological security in the center of China. And this is a large metropolitan area. And we measured we quantified urban ecological security, which is a measure of how secure and sustainable the environment is in this sort of metropolitan area over time from 1996, 2006 and 2016 using Landsat data, and then used those spatial variables, shoved them into a modeling process to predict how things are going to look by 2026. So we can do predictive analysis now of what likely change is going to take place in the future on the basis of spatial data inputs from now and in previous times. And in the present case, the rapid urbanization going on in this part of the world looks very problematic. You can see the red and the pink are the two most critical categories of morbid and danger in terms of urban ecological security. Right, so what else is good about these data? Well, they are, or many of them are free, okay, free to use. And for this, we're probably really grateful to the USGS, the United States Geological Survey, who in their wisdom in 2008 decided they were going to simply stop charging for their image data and make it freely available to everyone, not just US, but everyone around the world for sort of civilian use, well, for any use, because it was all there available for download. And the reason they did that, it was a great idea. And the reason they did it was because they realized that the vast majority of image purchases were being made by other US government institutions, you know, a lot, something like 90%, 95%, I can't remember the exact figure, but there was money going from US government to US government to fund this. So they thought, why not make it free? And by making it free, increase of Landsat data use went up by many, many orders of magnitude. And very quickly, we're into millions and tens of millions of downloads of Landsat data. So that was free from 2008, possibly as a result of that. The Sentinel mission, which was in the planning, was rendered into, or maybe there was a relationship between Landsat going free and Sentinel now being free. But whatever it was, the Sentinel missions from Europe are a kind of equivalent. They're a bit more sophisticated. There's more of them. They have different sort of sensors and different create different forms of imagery. Sentinel-2 is the sensor that I've shown you so far. That's the equivalent to Landsat. But these data are all free as well. So medium resolution image data is available free. And these are the data volumes in petabytes, so up to 4.25 petabytes of data have been downloaded in 2019. You know, these are serious numbers of free data that people are accessing and using. Or these are the data that are available. Sorry, this isn't the downloads or the uses. That's a much, much higher figure. This is the volume of data that is freely available. So I've talked about the medium resolution stuff quite a lot, Landsat-like data, Sentinel-like data. And on the left here, you can see a Landsat image. This is a Landsat image of an urban area. And you can see at this scale, where we're trying to zoom in and we're trying to understand the detail of an urban area, the scale is problematic. The resolution, the medium resolution provided by Landsat is problematic. It's really too coarse to identify the fine level of detail which we might want if we're to investigate urban areas in detail. And my thinking for you, for UNICEF, is that many of the applications you'd be interested in would involve people and perhaps settlements. So where people live, where they are, where they exist. And to get good levels of detail, like might be available from something like QuickBird on the right here, this is a 3.2 meter image, you need that level of detail. You need that level of spatial resolution. So QuickBird is an example of a very high resolution instrument, and we need to get to that level to make very good use of it. So the most high resolution imagery provided by satellites, you can get finer imagery from aircraft and drones, but the finest currently available is from WorldView 3 and WorldView 4. There's two sensors there which have the same instruments, so they increase the frequency of coverage, and the data are as fine as 31 centimeters. So that's a foot. That's about an imperial foot, 0.31 of a meter. Now, this image isn't actually 31 centimeter resolution, or it could be a pan-sharpen resolution, but the multispectral, the color images that you get are rendered at 1.2 meters, so 4 times bigger, or 16 times if you multiply to get the square area. The panchromatic band, the black and white band, is 31 centimeters, but you can actually pan-sharpen your image and integrate your 1.2 meter color image with your 30 centimeter black and white image to get a pan-sharpened pseudo color image of the environment. I don't know exactly what this one is. I suspect it's 1.2 meters. So you can get incredibly high levels of detail from satellites, not only from aircraft, not only from drones. But the problem, the traditional problem, since VHR imagery has been around, and it's been around for about 20 years, ICONOS was the first launched in 1999, and it was essentially launched as a result of relaxing legislation in the US and elsewhere after the Cold War ended. So this was ex-Cold War technology that was declassified, made available to the civilian sector, and a new generation of very high resolution instruments were born in 1999 with ICONOS. But since then, the data have been very expensive, and you might be easily spending $1,000, $2,000, $3,000, $4,000, maybe $5,000 to $10,000 on an image, which is, I don't know, 10 by 10 kilometers, so 100 square kilometers. So cost has been a real barrier, a prohibitive barrier for widespread use of these sorts of data. This has limited their use, especially in data poor or resource poor parts of the world. So some of the developing parts of the world in the global south, where arguably these resources are most vital, potentially where UNICEF is doing a lot of work, are the areas where there are constraints to getting these really excellent detailed image data because of cost. So some good news here. Now, it was my birthday 8 days ago. I'm not very good with birthday presents. I'm never very good at deciding or responding to anyone asking me, what would you like as a present? But I received a very nice birthday present 8 days ago from NICFI, Norway's International Climate and Forest Initiative, who announced their free release of VHR imagery, 5 meter resolution or better, of all of the tropics at least every month in an arrangement with Airbus and Planet and various image providers and suppliers and so on and so on. And this is very significant. Now, these data, these images, and I don't know exactly what level of processing the data will have. So they might just be images that you can look at. They might not be analysis ready data where you can do meaningful digital analysis, but we all can get some of these data in some form. And they've promised monthly updates of all of the tropics. And you can see the footprint here that's covered by this. The intention behind this is to monitor forests, because Norway, or this particular initiative, is so concerned about forest loss and what this means for the global environment, and rightly so. But the footprint you see here is the area that's covered. So these data, this imagery, this 5 meter imagery, will be available for all of these parts of the world. And I'm guessing that, you know, some forested areas, but also non-forested areas in these parts of the world, in global south and developing countries and so on, I hope are of particular interest to you. And they're of interest to me in my environmental analysis as well. So really good news. And this is the way things seem to be going. You know, there's much better data out there, and it's gradually being released and made available to us free of charge, or at least low cost. So I think these data are really good for you. I think this removes one of the barriers, one of the significant cost barriers, and makes it immediately accessible. These data are immediately accessible and usable without that constraint. So let's think of another example. I've tried to put in the odd example here. I think it will be of particular interest to UNICEF. And one area is refugee camps. Now, I remember seeing work about this when Iconos came about 20 odd years ago, when the first of these VHR sensors was launched. At last, we could see the detail of refugee camps. And it does, the VHR imagery, the very high resolution imagery. This is Zatari camp in Jordan, one of Toby's old stamping grounds. You can see great detail. Actually, perhaps should have zoomed in a little bit more here, but you can see the construction, the outline, and some of the detail within this new footprint of a refugee camp and how it's growing over time. And when you zoom in, you can see lots of detail about the shelters and the settlements and the resources that are there. So through images, you can see these things. To start with, you can see these things. And this is viable because of the VHR imagery that we now have access to. I would say, I think, and Toby and Attila suggested I raise this point, there are ethical issues related to use of data like VHR data. The level of detail is very, very high and enabling you to see incredible amounts of detail about the human features and even the humans themselves on the ground. This is a graphic of Harbourside Market, Wellington. This is, I think it's an aerial photo, but in Wellington, New Zealand. And you can see the people. You can actually see the people themselves. And I think we've got to be very careful about using these data and about use of these data around privacy, but especially perhaps around security. We've all got to, consider GDPR issues these days as well. And I think very serious discussions must be had about the way that these data are used and the way that information derived from them is considered and served up to other parties. So thinking of an equivalent, something like census data. In the UK, census data is captured at household level, but then it's aggregated spatially, and it's only served up, and it's available, it's public, it's free. I can access it, I can get socioeconomic information about the population of the UK, but it's only served up at aggregated spatial units. Enumeration districts or output areas, I think, are the finest unit. And that is a collection of households averaged over a certain area to anonymize things, to make sure that individual and potentially concerning security and privacy information is retained. And this strikes me as being an extremely sensitive issue for you, for UNICEF, for safeguarding people. In many instances, you perhaps wouldn't want information out there about the presence of individuals and populations in certain parts of the world for whatever security reasons are going on. I'm going to leave data ethics to you. It's not something that I, in my research, need to engage with too much. And actually, on that, I think I'll just completely hand it over to UNICEF and Attila and Toby to deal with this lecture. They tell me they're putting it up on a SharePoint site. There's talk about it going on to YouTube. I'm perfectly happy about that, but there's copyright issues and ethical issues about using information extracted from the web, which is what I've done here. So, I'm not washing my hands of it, but I'm handing over responsibility to you. So it's one thing I don't have to worry about. But these ethics are, clearly a very serious concern for when using very high resolution images. So back to refugee camps. This is Tongo refugee camp near Sudan, near the Sudanese border in Ethiopia. It's one of the largest camps in Ethiopia. And the previous image I showed you, Zatari refugee camp, we could see the structures physically, but that only goes so far. Typically, it's necessary to integrate image data with other data. I'm going to talk a little bit about reference data later on, but you might well need more information to arrive at useful and meaningful information. So for instance, if you're using imagery to try and estimate populations in refugee camps where they're changing rapidly over time, over weeks, over months, with an image, you'll be able to see what's there. You could see people, but let's say typically you don't see people. You don't have the resolution of an aerial photograph. If you've got something like an Iconos image, you can see structures, but you can't see individuals. So you could see the number of structures, the number of huts or houses or shelters or tents, and you could calculate their size. What you don't know is how many people are within those. So if you can get sample information, for instance, identifying a typical number of people residing in any one of those structures, then obviously you can aggregate that, you can sum that up and calculate, or at least estimate with a reasonable amount of accuracy, the total population. So typically, I suspect you will need additional data to get to the very detailed human information, the human answers, rather than just the physical lie of the land, which you can get from imagery. So,
Paul, it's Toby. Sorry to jump in. We've got about 15 minutes left.
Yeah.
So I would suggest maybe another 5 to 10 from you, and then we can open up for questions.
Okay, no bother.
Super, thank you.
Okay, so in terms of systems to undertake the sort of spatial analysis, geospatial analysis that you might want by integrating spatial data, other spatial data, ancillary data with imagery. GISs are now very ubiquitous. I'm assuming many of you will have heard of GISs, and they're free. So I show QGIS here. This is just one example of a free online GIS package, but the tools are there to use these sorts of things. In terms of accessing the data, certainly the medium resolution Landsat and Sentinel data, these are all available readily, easily on the web using web-based applications and repositories to download data. So this is USGS Earth Explorer for Landsat, or Sentinel Hub for the Sentinel data. And you can use systems like Google Earth Engine to not only get the data, but to process them using a very wide range of advanced functions. And this is cloud-based, so you don't have to download and hold all the data locally with you. And recently, the most recent generation of remote sensing gives you information. Doesn't just give you data, it gives you calibrated, pre-processed information products. These are things that we weren't able to take for granted in the past, but now the remotely sensed information is much more usable by non-specialists. Okay, so I think they're more accessible for people who don't have this specialist knowledge, and hopefully within the UNICEF community. Another final example of the sorts of applications I think that you might be interested in, things like disaster response. You'll be very familiar with sort of meteorological images showing you paths of hurricanes. This is Hurricane Ike back in 2008, making its way through the Caribbean. And these are aerial photos showing you the damage, and captured quickly after the episode. This sort of thing is used for relief efforts. Now, as well as the imagery, I talked about needing a reference. Typically, remote sensing needs checking through a different source of data. And usually this is field-based. And I just couldn't resist showing this imagery. This is Toby Wicks. Toby and I did our PhDs together in Southampton many years ago, and he assisted me on my PhD research. So this is field note-taking. This is land cover survey. A few other graphics around other reference data of a satellite image from aircraft, and then the other sort of ancillary data, interviewing farmers, taking records of what's in each of the fields. These other data are needed to to calibrate the imagery. And the final example I was going to show you was of my own work in Sansan Ponsac in Panama, to talk about the fieldwork we have here. And the reason I was going to show you this, I'm not going to show you this now. I might play it at the end when things die down, but I have a video, my favorite video from all of my fieldwork around the world is of this sloth, which was very, very slowly attacking the car. And in the video features this hard copy remotely sensed image, which was used to roll away the sloth from the underside of our 4x4. And just to remind you, my definition of remote sensing, staying as far away from the problem as possible. This image did exactly that. It kept the sloth away from us. Right, that's it. I'm going to leave it there. I'll leave you just with a lovely quote I have. Man must rise, or let's say humans must rise above the earth, to the top of the atmosphere and beyond. Only thus will they fully understand the world in which they live. So remote sensing is relatively new technology in human terms, but the sort of idea of this ability to synoptically monitor the landscape has been around for a very long time, and as long as 2,500 years ago. Okay, thank you very much.
Absolutely wonderful, Paul. Thank you so much. For those of us listening in, let's just take a minute to take ourselves off mute and give a big round of applause for what was quite an impressive presentation. Absolutely phenomenal, Paul. If you need a second to grab a glass of water, please do. We'll now have 10 minutes or so questions and answers, and hopefully we'll get a moment to see the video that you tantalizingly showed to us just there. There've been quite a few questions on the chat as you've been presenting. Some of them are more internally looking at UNICEF, but given time is tight and we're fortunate to have you with us, Paul, I'm going to prioritize those questions that are really quite specific and best answered by you first, and then we'll see how much time is left. Interesting that there's been a couple of questions on drones. Let's ask the audience, if you're particularly interested in having a separate session on drones, please write yes in the chat and we'll make sure that that happens. A very specific question from James. Paul, you mentioned cellular autonomy for the predictive applications in the China example. Can you suggest more software tools to explore this? Number one. So park that for a second. Then Lars is asking a broader question about UNICEF, and I think that'll be an interesting one if we get time to explore. Secondly, Do Hyung is saying, it's clear there's loads of progress in terms of availability of remotely sensed data. However, applications, I feel, are not necessarily catching up at the same pace, particularly in humanitarian organizations like UNICEF. Paul, what do you think are the bottlenecks in terms of integration and use of remotely sensed data in some organizations? So there's a couple of questions to kick us off. Paul, your thoughts on those, very much welcome.
So I think cost has been a problem. Cost has been a major bottleneck, just having the resources to get the data. And this is the picture is improving here. We've got free medium resolution imagery, and we've started to get free very high resolution data, which I think is of more immediate use for UNICEF. So that's on the way to being solved. The technology has always been a bottleneck. For a long time, the instrumentation and the volume and sophistication of the instruments that were, orbiting the Earth were quite limited, and we just couldn't get enough data for the purposes that we wanted. We then got all the data because we got more and more instruments being launched and so on. And then the bottleneck was getting the data in a usable state. There was probably about a decade when we had a ton of data, but we couldn't get it to the users because we were still sending CDs out to people from suppliers and things like that. So there's been a massive effort in the last decade and a half on data dissemination. And this is now, this is why we now have these online services where you can go and get the data. And Google Earth Engine has absolutely revolutionized this. I don't want to be proprietorial. I don't want to push one particular company, But Google Earth Engine has done real wonders for our game because it provides access to a vast volume of data, but also because it's cloud-based and it's got its processing routines. You can use these data, and there's now I went to a conference last year. I'd been, because of childcare, I hadn't been on the international conference circuit for 2 or 3 years. I went to a conference in Italy last year, and everything was about Google Earth Engine and people using stacks of hundreds or thousands of images for a single piece of analysis, because Google Earth Engine made this possible. So the amount of temporal information, the change over time that we could use to increase the accuracy of the information that we're getting was absolutely incredible. So I think cost is being tackled. Data has been tackled, and data access has been tackled. I think the bottleneck now is user awareness and user skills, and that's why I think this webinar is quite a good idea. I think you need to get the message out there, and hopefully this is helping. This is hopefully helping a little bit, but you just need more of this. These tools are now accessible by non-specialists, and there's a lot out there for use. So please use it.
Super, Paul. And then just on the China example and the any thoughts on that one specifically?
No, it's not really my area. We use cellular automaton. I have used it in the past a little bit. We use Markov chain modeling, neural network analysis, and stuff like that. There are no doubt a handful of approaches, but I'm going a little bit beyond my own skill set here, and I'm reluctant to start saying words about which I kind of know, but I'm not very, very familiar with.
Do you know any names of people who are leaders in this field that James could reach out to? Not now, but maybe.
Yeah, get back to me. Yeah,
that'd be good. Thank you. Interesting question from Glenn. So Glenn is saying a conceptual question. One definition of remote sensing or excludes information gathered via seismic or sonic sources. Any particular thoughts of that? Measurement of sound waves generated underwater earthquakes. Give us some insight into historic sea temperatures. Change in foot traffic in Manhattan resulted in measurable seismic changes pre and post COVID. Thoughts on that, Paul?
It's a semantic issue. I mean, to me, that's a form of remote sensing. I'm not going to be precious about what is or what isn't remote sensing. I'm an optical electromagnetic energy remote sensor myself. I use multispectral imagery predominantly to do sort of land cover, principally land cover analysis, and then use what's on the land to derive lots of other information.
Yeah.
But no, these are, I mean, as far as I'm concerned, these are just different forms of remote sensing. I don't know a lot about them. I can't say a lot about them. But where they're of value, so seismic data is obviously extremely valuable in earthquake disasters, in predicting, as well as any potential response to these things. But prediction is particularly important here. So yeah, there's a role for them to play in, if the shoe fits, wear it.
We've got a little over 3 minutes left. Another 3 questions. I will ask Nima for, if you wouldn't mind, Nima, posting a couple of links in the chat. So there is an informal geospatial group on Yammer. Nima, if you could please post that link into the chat so folk online can join that if they're not already members, to continue the conversation there. We also have a data help desk. As Attila said right at the beginning of the webinar, this is part of an initiative in terms of providing a guidance mechanism to colleagues on data collection. And Attila is in the process of recruiting a dedicated staff member to host and to act as the headquarters focal point to join the dots, if you will, on data collection efforts in and around this space. So that's imminent. We also have the data help desk. So Nima, if you flick a link also in the chat there, then colleagues, if they have specific questions, can use that to reach out if we run out of time. In addition, I think I saw Jan online. Jan, please do share links online to UNICEF's geospatial roadmap for colleagues that haven't seen it, which goes some way to answering the strategic question posted by I can't remember, was it Glenn or Lars earlier, and I'd like to get to that if we get a minute. But Paul, while we have you, last couple of questions in the last couple of minutes. Hopefully we get a second to view the video as well. So plenty of compliments also coming through, but a couple of specific questions. What about remote sensing to analyze atmospheric pollution, mapping of flood-prone areas? What are the best satellite data you'd recommend to do such sorts of analysis? But also, any particular thoughts on organizations that have successfully internalized remote sensing, and any sort of magic bullets or recipes for making that happen? Thoughts on those two, welcome.
Right, hold on. I'm just trying to find information on the first question there. So I've just got involved in a new project. I'm a sort of junior partner on this, a Royal Society project between the UK and China. And we are measuring, or we are trying to develop approaches to better monitor atmospheric aerosol pollution, and the gist of the project is that there's a new Chinese sensor called Fengyan 3D Mercy 2, MERSI, and then II2, which is serving up much more detailed spatial resolution. It's 250 meter spatial resolution to derive aerosol, atmospheric aerosol measurements, which is a step change better than the currently best or most detailed spatial resolution imagery used for aerosol monitoring, which is MODIS, which is the certain spectral bands from the US's MODIS satellite. So MODIS is MODIS, moderate moderate resolution imaging spectrometer. But the aerosol relevant bands of that image data set, different layers of imagery, is 3 kilometers. Yep. So there are a couple of suggestions there. I mean, I'm happy, by the way, for people to hit my email address just to chase these things up, and I can reply directly to them about.
Excellent. That's very, very kind. I think we've nearly addressed the conversation about some of the challenges or the organizational challenges to use remotely sensed data. An interesting question related is many UNICEF country offices, of course, are working hand in glove with government agencies. Any particular thoughts on how best to partner with government agencies on remote sensing in a couple of words?
No, not really. No, actually, I would flip that around and I would ask you for advice on that. I'm no diplomat, and I'm no, I'm an academic. I'm a researcher. I have collaborators and partners around the world, and I know individuals from different space agencies in different countries, not just in the UK. And certain countries are very amenable. So European Space Agency is very good and very engaged and wants people to use data and wants to use imagery for environmental and social security. The UK is quite amenable, but how do you go about setting up a collaboration? I imagine that local conditions will really determine that. If you don't know anything about remote sensing, you don't really know where to start, it might be worth trying to team up with some specialist in country. There will be remote sensors, there will be remote sensing researchers in all of the countries around the world. And if they're worth their salt, if their heart's in the right place, as most academics still are, despite the pressures that we're under. I mean, the educational sector is not a happy one to be in, certainly in the UK at the moment, in the sort of media pressure and governmental pressure on us. But, academics generally are still, half decent people. They're good people. They want to do research and they want to do things which are of value to society. It's important for research that it has societal impact. We're now judged as much on impact as we are on the research findings themselves. So maybe teaming up with in-country academics, if you're a real beginner to the subject, is a way to kind of move the conversation forward and maybe get a way into the data providers and the national governments and space agencies and so on.
Thank you so much, Paul. We're out of time. And as you say, given the pressures that academics are under at the moment, we are so grateful that you've managed to carve out some time to give us a super presentation. Feedback in the chat has been outstanding. So thank you for the presentation. Many people have asked, will it be available? Nima's already shared a link in the chat to show where that can be accessed after the event. So thank you for that. I will pass to Attila very briefly just to signpost what's coming next week. And then for those who can stay on for a couple more minutes, let's try and see Paul's video of remotely sensed data in action in its broadest sense.
It's worth seeing. Really.
So Attila, maybe pass to you if I can to tee up next week, and then we'll come back to Paul for his video.
Thank you so very much, Paul. This was a great presentation, and I would like to thank everyone for their participation and the great questions and comments. I just wanted to mention that next week's webinar will be on high-frequency phone surveys by Talip Kılıç from the World Bank. And before we see the video, I wish you all a good time until next week. See you here next week at the same time. Please stay healthy and safe. And let's watch the video.
Super. Okay. Thank you so much, Attila. And just before Paul shows us the video, it's clear that, you know, I didn't use the word before, but UNICEF is quite immature in terms of the use of remotely sensed data and geospatial data in general. So it's a good start to this conversation, and let's continue it online. And with that, Paul, thank you so much. Over to you to send us off with the video.
Okay, so I hope this works. Windows, let me find it. Here it is. So remember my remotely sensed image, and remember my definition, staying as far away from the problem as possible. Let's give this a go.
Here's a little sloth.
Can you see this, Toby?
Yeah.
Yes, we can see it, Paul.
My narration is not very expert. You'll find I'm no expert when it comes to the animal kingdom. But at this point, I was concerned the sloth was very slowly attacking the car. And the danger was, if you see the claws of the sloth underneath the car, it had quite high clearance. So we were worried about it getting to the underneath of the car, to the sump, and having a go at it. So we didn't really, it was fascinating to see this animal, but we didn't really want it climbing underneath the car. There's a silhouette of the image. Remember, remote sensing, staying as far away from the problem as possible.
Oh, poor little guy. Come on, mate. Poor little fella.
Okay, all done.
Wonderful. Thank you so much, Paul. Thanks, colleagues, for joining. I appreciate there have been many competing meetings at this time, so we're grateful to all of you for joining us, and we'll see you online again very soon. Thanks again, Paul. We'll keep in touch.
Yeah, thanks all.
Thanks, Paul. Bye, everyone.